Well, in the last part on the Smith chart part 2, we saw that we got family of circles in the gamma plane inside the disk, inside the gamma disk. So we want to get familiar, we want to see what that algebra actually looks like. And I'm going to show you the families of R circles and X circles and the position, and then we'll just discuss it and you'll be able to see it graphically. So this is our first application, view of Smith chart. So let's have a look. Well, here's the chart, and you can see these circles here. There's one, here's another one, and that one goes through the center. That's R equal to 1. And then as the circles become bigger, their labels, this is the R equal 2 circle. And the other family of circles that that we have done in class are these ones, and these are the X circles, the reactance circles, and they're positive on the top and negative on the bottom. So in terms of impedance, this is going to be inductive, positive reactance, and negative reactance. And now, for example, I've drawn concentric with the point 1. Remember, that's the center of the gamma circle. That gamma circle is sitting at 1, 0. And that gamma circle has at a maximum a radius of 1. So you can't get anything outside this. And here's an example of a gamma circle whose center is 1 and its radius is 1.5 in terms of radius units. Now if you think about this, the radius of the big gamma circle is 1, 0, 1. It's a circle, so that's 1 to 2 here. And the radius of the R equals 1 circle, which is this one, and it would continue around to here, it actually has a radius half that. So its center is about there. So 1.5 and 1.5, so right there. So this is going to be a reflection coefficient that's less than 1. Here's a point that has the R. So in this case, R is 0.2, sitting on the 0.2 R circle, and J is X, reactance. It's in inductive 0.5. 0.5 J plus 0.2, so R 0.2 plus 0.5 J puts us there. Now if that was the normalized load impedance, we would be able to move around and see how that changes as we go up and down the line, because as we move, that point rotates on a constant radius circle. So what we do, and we'll see this in the examples, is we take this point, join it with a line there, draw a circle. That would give us a circle that goes around, slightly larger than the red circle. Then we'd move around on that circle, and then instantly we get the impedance, the input impedance, as we move away from the load. So that's the dynamic part. Brilliant thing by Phil Smith. Now let's see if we can put up the actual chart with all the details. This is a chart where everything wasn't plotted densely, so I'll just bring that up. We'll find it somewhere here and go down, and here is an example. There it is. That's the main Smith chart. You can see, I'll do some magnifications, and we'll scroll down, and you can see here, here's the R equal 1 circle. Comes around, there it is. And you can see the detail, right? It's much more densely sampled, and it's actually really hard to draw this on a computer, because if you don't do it right, things can get pixelated in a hurry. I'll show you. Oh, this one's done pretty well. I've been blowing it up, and that's about 6,500 times, and this was done in a very special way using arcs of circles. So now we got our introduction to what the Smith chart J and X, R and X circles look like. We know where the position of normalized impedances are. We are starting to get an idea of how to move around, and now we'll continue to use this and start doing a bunch of examples that use the Smith chart, and that you'll see how incredible it is.